Okay, so my Croatian is not great, but I know he was talking a bit about philosophy and physics. It might seem odd for me to be giving a talk inaugurating a lecture series in the philosophy department, but I just want to start by reminding everybody that the great philosophers of the past all were very deeply concerned with what we would now call physics. Aristotle was, Plato was, I mean, not as much as in the Timaeus. Certainly Leibniz, certainly Descartes, certainly, right? All through that period, Newton was a natural philosopher, called himself a natural philosopher. And as I like to say, everybody gets a PhD, namely a doctorate in philosophy. So the questions I'll be asking why, and talking about why in what I usually call the foundations of physics, some people call it the philosophy of physics. I don't really see much of a distinction there. They're very deep, fundamental questions, in this case about the nature of the world, and ones I'm going to try and convince you we have not yet gotten to the bottom of. Philosophical tools of analysis and careful thought can really be of great assistance. So there's this picture. When I made this, I knew I didn't have to draw this picture, that if I just went on the web, I could find a picture like this, and bang, there it was, so I didn't think of this. There's a normal story that's told that modern physics rests on two pillars. Sometimes, I mean, actually, sometimes people now say three. I was going to put up three and then knock one out, but I figured I'll just save time and only put the main two. One is, are the theories of special and general relativity, really general relativity, and the other is quantum mechanics. And just at a very large scale, you could think of it this way, that this pillar is about the structure of space and time, or what we now call space-time, and this pillar is about matter, the stuff that's in space-time, that we can actually directly see and get empirical access to. I mean, in some sense, you can't directly see space-time itself. You only infer what it's like as part of an explanatory project to explain what you can see, and that's always matter or something like that. Now, the interesting situation we have, if we have these two great pillars, is that everyone agrees there's some kind of tension here. For some reason, now it's happened, sorry. Figure out. There we go. If I have to do it that way, I'll do it that way. So by fundamental physics here, again, I mean that part of physics that goes down to the bottom level. There's lots of other sciences that are concerned with nature, but don't even pretend to be at the bottom level, right? Biology, for example, lots of interesting things to say about biological systems, but ultimately we would say biological systems are chemical, right? We understand somehow DNA, for example, in chemical terms, and chemistry is in some sense ultimately physics, and you sort of analyze your way down, and you finally get to a bottom part that's not analyzed in terms of anything else. So what is physics about? Well, I think a good place to begin is just a simple definition that it's the theory of matter in motion. You immediately see, if that's true, why physics holds a different status with respect to the other sciences. Because every biological system, whatever it is also matter in motion. Right? Every geological system, whatever it is also matter in motion. Every cosmological system, every astronomical system. You might be interested in plate tectonics, so you're not interested in all of physics, but every subject matter of the special sciences, even economics, whatever else it is matter in motion. Sorry. Not working so well. If that's true, then of course there are two immediate targets of inquiry that you can ask: what is matter after all? And what is motion after all, fundamentally? And once you have those answers to those two questions, then you can ask, what are the laws of physics that determine how the matter moves at the most basic level? That's how it changes at the most basic level. Really haven't. I'm sorry about this. I don't know why this is.
Motion.
Yeah. Well, I mean, but usually I could. There we go. All right. So, what kind of answers might we imagine could come to questions like this? For what is matter? Here's an obvious one. It's made of microscopic particles. This certainly goes back at least to Democritus and his theory of atoms. Newton thought that ultimately matter was what he called corpuscles, little bodies that moved, that otherwise did not change. I mean, that was the point of Democritus. The atoms couldn't be broken, they couldn't be split up, they always had a fixed geometrical structure. All they did was move, bang into each other, bounce off each other. Newton had a similar idea. Of course, he didn't have contact forces, but Newtonian forces like gravity. But still, that was a basic picture of matter. Once we got to electromagnetic theory in the 19th century, a new proposal was made that there's something else that things are made of, or part of physical reality, which are fields, electric fields and magnetic fields. Now, when they started this whole business with Faraday and so on, they had the mathematics of the fields, but they didn't really have agreement about what they were. So, for example, some people would say, well, gee, if there's a field, there must be some matter there, right? Like these are stresses and strains in the field, what we're seeing. And then you needed they thought you needed a mechanical account of what the field was made of. But eventually they gave up on that. There was all kinds of trouble trying to create a theory of a luminiferous ether or some field for the electromagnetism to be in. Eventually they gave it up and said, no, we'll just accept that at a fundamental level, there are fields. They, unlike particles, are not located one place or another. They're always everywhere. And their change is not locomotion, it's not change of place, it's change of value, right? The amount of field or the direction of the field can change. Nowadays, you'll hear people say stuff very much in the tone of voice of Thales or Anaximenes. Ultimately, everything is strings, like little vibrating strings, and if it vibrates this way, it's an electron, if it vibrates that way, it's a quark. So you can recognize the kind of answer. There's the idea that somehow quantum theory tells us that at the very bottom level, we don't have the right conceptual resources to think about what it is. It's a sort of something that's kind of a particle and kind of a wave, but not really a particle and not really a wave, or sort of sometimes it's one, sort of sometimes it's another. I mean, there's all kinds of more or less gibberish. You'll hear about this that goes under the banner of the Copenhagen interpretation. So that's possible ways of thinking about what matter is. What about motion? What is motion? Well, Newton said there's a thing he called absolute place, that there was this one big three-dimensional Euclidean space that persists in time. At any moment, any particle is somewhere or other in that absolute space, and what the particles do is they change their absolute positions or remain at the same absolute positions. That gives you absolute motion, absolute velocity. People don't much like that anymore. I'm actually kind of a big fan of that, but that's another story. And they say, well, the right way to think of it isn't that way, but imagine space-time as some big four-dimensional object. And then the trajectory of a particle is like a line or a space-time worm. Remember read Kurt Vonnegut, the Tralfamadorians see the world that way. So we look like these long, skinny worms that move through space-time, and they can kind of jump in different parts of them. That leads to the question, well, if that's right, well, what is space and time? Or if you're going to put them together into one object, what is space-time? What kind of structure does it have? And again, Newton says, well, it's three-dimensional Euclidean space, that's the spatial structure, and that the individual points of that persist through time. And time is a one-dimensional thing in the sense that a single number will tell you what time it is at any given moment. When you get to the special theory of relativity, that changes the picture. If you understand it the way Minkowski did, and you say, no, it's really a big, single, four-dimensional, unified object that has a certain geometrical structure with light cones in it, that isn't at all what Newton had in mind. And then by the time you get to general relativity, you say, well, in fact, if I take this space-time, which in a certain technical sense is flat, but I now allow it to have curvature, then I can even explain the orbits of the planets, I can explain why apples fall, I can explain all of the phenomena that we call gravitational. So that would be places that we get to by pursuing the question, what is motion, what is space and time? How does matter relate to time? Again, I said this, but I'll say it again. For the particle theory, where every particle has a definite position at any given time, the particles, furthermore, are supposed to persist. That is, they don't just jump around. They don't suddenly disappear here and show up there. And therefore, they move continuously, and then we get this idea of their trajectories being a space-time worm. But if instead we think about fields, you can't talk about them locomoting because they're always everywhere, but we can talk about disturbances in them moving in the way that we look at water waves and you say, look, you seem to be tracking a single wave in the ocean, and you say there it's going that direction at that speed. But at a fundamental level, that's not what's going on. That is, no little bit of water is moving that way. Actually, the little bits of water, strangely enough, are doing little tiny circles. But in virtue of those circles, the lumps in the water can move in a certain speed, in a certain direction. And then, if you have a field theory, you can say, but what about those particles? You have two choices. Maybe they're particles in addition to the fields. Maybe the particles are really just states of the fields themselves. So this was an idea that goes back a long way of saying if I've got these fields, maybe some kind of singularity or vortex or something in the field creates or is a particle. Those ideas have been considered by physicists. Again, if you go with string theory, well, the way they talk about it is as if you just have strings, they persist through time, and as they persist through time, because they're one-dimensional, they don't just move, but they can vibrate, and that's more or less the way people talk about that. Now, if you're thinking about physics in this way, again, at the very deepest fundamental level, you say, I'm going to specify a physical theory by specifying a few things. I'm going to specify a space-time structure. I'm going to specify an account of what we can call the local matter, or what John Bell called the local variables, which is what exists in that space-time that can be located. So I can point my finger at it, right, and say, what is it here? What is it here? If I have particles, there's a perfectly good question. How many particles are here? How many here? If I have fields, there's a perfectly good question. What's the state here? What's the state here? So these local kinds of things are what we're going to use to build up a picture with tables and chairs and cats and people and stars and planets and everything else as large conglomerations of these local things. Now your theory may have, in addition, other things that are neither space-time nor are they local variables, that you postulate, well, why would you postulate some other kind of thing? And the answer is because, remember, at the end of the day, we want to write down some equations, some dynamical equations that govern how these things behave, and you add whatever you need to account for what you see. Now, it turns out in quantum mechanics, you add a very strange thing that there's a lot of debate about called a wave function of a system. Whatever it is, or whatever it represents, it's not a local kind of thing. It's not the kind of thing that, as John Bell would say, I can't point my finger here and say, what is the value of the wave function here? That just doesn't even mathematically make any sense. It is not a local kind of object. That ought to puzzle you, puzzle a lot of people. A lot of people wanted to get rid of the wave function because of that. But it turns out that very lack of locality, which lies at the center of quantum mechanics, has consequences. You really can't get away from it. And the rest of this talk is just about why you can't get away from it, why this creates a problem. So once I have all this in place, then I write down my dynamical equations, and I'm restricted in those equations to mentioning just these things that I've postulated. So you see how this thing all holds together as a kind of architectural structure. Good. So back again to relativity and quantum theory. We need a theory of space-time structure and a theory of matter and whatever other fields we might postulate. And we want to articulate the dynamics in terms of the space-time structure. And the two great pillars are, as I said, the two best things we have at the moment, the theory of relativity and quantum theory. And then you might say, but if that's the story, how could there be a tension? How could there be a conflict between these two pieces? It seems like they're just independent parts that go into this kind of recipe. Well, there's one kind of tension that you could have between them, which we call the lowest level. It just might be that you have one of these theories articulated in some mathematical form, the other one articulated in a different mathematical form, and those two kinds of mathematics don't play together well, right? There's no obvious way to merge them into a single theory, right? That, of course, we need, right? At the end of the day, there better be a single theory because there's only a single world. It does what it does. Physics somehow knows what to do in all circumstances. You can't say silly things like, oh, when objects are big, they follow these laws, and when they're small, they follow those laws. Or when there's not much gravity, they follow these laws, and when there's a lot of gravity, they follow those laws. Because those are not sharp distinctions, right? And there are certainly circumstances where both gravity and the other forces are all playing very large roles. All of this has to be somehow merged together into a single theory from which we expect, under certain restrictions and in certain domains, general relativity emerges as a good approximation. Standard quantum mechanics emerges as a good approximation. If that were the tension between these two, then you could say it's just a technical mathematical issue. As I say, you might, if that's what the issue were, you could imagine waking up one fine morning to the headline, problem solved, right? Some clever mathematician has figured out how to adjust or re-express each of these theories in a way that puts them together, and that would be the end of that. Okay? Now, the main point of this whole talk is that's not our situation at all. Okay? The problem here isn't like that. And it's not going to go away by some clever mathematical trick. The problem is much deeper, much more profound. And it takes the form as I would say, essentially, in some normal way of putting it, a straight contradiction between the two theories, at least as they're normally understood. And contradictions don't just disappear. So what's basically the issue of this contradiction? The theory of relativity, as it is always presented, is supposed to imply or state that, quote, nothing goes faster than light. The speed of light is some absolute physical limit of how fast anything can go. I always said there's a wonderful story. John Bell, and this is all going to be about Bell's work, tells a story about he was once giving a talk on a campus and they had all these posters back when they had actual physical posters. And the title of the theory was, "What Can't Go Faster Than Light?" by John Bell. And he was walking over to give the lecture and he noticed someone had put some graffiti on a poster and he goes over and looks at it and someone has written, John Bell, for instance. Can't go faster than light. So that's on one side. On the other side, we have a theorem that John Bell proved, known as Bell's theorem, that says that there are certain observed correlations in the lab, just things you can go into a laboratory and test for, that cannot be predicted or explained. It's impossible to predict or explain them if no causes at least go faster than light, if causation or the notion of influence is restricted to the speed of light. And so, this is a real problem. And in a way, well, that's not yet a problem. This is a mathematical theorem. So Bell says, if you see such and such in the lab, you have to have causes that go faster than light. Now the real problem is, first of all, that quantum theory predicts the kind of thing that Bell says can't happen if nothing goes faster than light. So that's you can already see that there's a kind of theoretical conflict here. But in a way, I'm going to say that conflict has also been resolved because we did the experiments. And independently of what quantum theory predicts or whatever, you just see this in the lab. So if somebody's got to give here, it's got to be relativity, at least relatively understood as saying nothing that goes fast. And the rest of this talk is just to explain how all that, the logic of that works. I should mention here that there's a kind of conceptual, it seems to me, confusion. As I say, everybody says, this theory of relativity says nothing goes faster than light. People also say the theory of relativity asserts that the speed of light is constant. Notice, these are different claims. I actually want to say this claim doesn't even make any sense. It's not that it's wrong. It's just that there just isn't, according to relativity, there isn't anything that counts as the speed of light. Objective speeds just don't exist in that theory. But despite that, you can make perfectly good sense of this first one. And all of this, I'm just going to illustrate kind of visually, right? As this is what I just said. The correct description is there are no speeds in the theory, but nonetheless, light can, as it were, form a kind of limit. If you want objective speeds, then you have to go way back to Newton. Newton had absolute speeds. Newton had absolute space persisting through time. You could talk about how fast and in what direction something was going objectively. But by the time you get to relativity, you've thrown away the conceptual resources you need to make claims like that. All right, so let me just talk for a minute about what Newton thought, because what Newton thought was what everybody thinks offhand, right? Newton's picture of all this, although he cleaned it up mathematically, at a deep level is very familiar and intuitive. It's the way everybody thinks about this. He thinks, first of all, as far as the time structure. Well, there are instants or moments of time, right? There's one. Here's another one. The first one came before the second one. And that these instants of time are global and universal. So I have a quote, I think, coming up. So you can ask, on Newton's account of time, it's a perfectly good thing to ask. At the very moment when I snapped my fingers, what was going on Mars? What was going on Alpha Centauri? What was going on in some galaxy far away where we know that we don't know what's going on, and furthermore, we can't find out for a long time, because we'd have to wait at least for light to get to us to figure out. But nonetheless, something was going on at that very moment, so there's this nice quotation from a paper of Newton's called De Gravitatione, when he's talking about time, and he says, we do not ascribe various durations to the different parts of space, but say they all endure together. The moment of duration, right, the instant of time, is the same at Rome and London, on Earth and on the stars and throughout all the heavens. Right? You couldn't say it more clearly than that. An instant of time is a globally defined thing. That means you can perfectly well ask of any two events, one on the Earth and the other on Alpha Centauri, which, if either, came first in time. Maybe they happened exactly simultaneously, so there's absolute simultaneity in this picture. Any two events, either A occurred before B or B occurred before A, or they occurred at exactly the same. That's the way we think about things. Once we have these instants of time, we can stack them up, right? We think that these global instants of time then succeed each other. There's between any pair of events, a definite amount of time elapses. That's what Newton would call absolute time. And all of these would have objective answers. Whether we can determine those answers empirically is a different question, but on Newton's picture, there certainly are correct answers to things like that. So we can stack up these things. Now, since space is three-dimensional and time is one-dimensional, if we stack up all these copies of space, we get a four-dimensional object, which we can call space-time. Now, I haven't done anything very fancy there. I haven't really done anything. I haven't changed the picture at all. It's just a way of thinking. If you say space-time is four-dimensional, you say, I mean nothing more than that to locate an event, I have to give you four numbers, a latitude, a longitude, an altitude, and a time, right? It will be different for that one and different for that one. People often say, well, in relativity, time becomes just another dimension of space. All of that's false. Okay, that's not true. The idea that space-time is somehow four-dimensional, on the other hand, is really quite trivial. I can't draw pictures of a four-dimensional space-time because I can only draw three-dimensional pictures, so what we always do is we suppress one of the spatial dimensions. And so I can draw pictures of what we call 2+1 dimensional space-time, a two-dimensional space with time. You could think of it as the world of a little flatland creature who has to stay confined to a two-dimensional plane but can move around it. Okay, so that's what these pictures are going to look like. Again, what at a certain moment Newton thinks space is always three-dimensional with a Euclidean structure, and furthermore, that the individual points of space themselves persist through time, so it's a perfectly good question to ask whether this event happened at the very same spatial location as that event. If they did, then you can think there's no motion between those two. If they didn't, you can ask how far apart they were, in what direction, and then you get these absolute velocities. And so we have, for Newton, absolute definite objective speeds of things. As I say, this is actually going to go away. So here's a picture of Newton for this two-dimensional space. What I've indicated here, P and Q are points of absolute space. So they never change with respect to each other, because they're just 2 points, as it were, in this two-dimensional space. Then I have A and B. You can think of these as billiard balls. They can move around. And I'm just showing at time t equals 0. Oops. Boy, if I do it that way, maybe that will solve all my problems. Anyway. How I went back. So at time t equals 0, A is near point Q and B is near point P. And as time goes on, you see the two billiard balls, or billiard discs in this case, are approaching each other, and here they bang into each other, and then they reflect off. So this is a kind of picture of that kind of interaction. And because between t equals 0 and t equals 1, there are an infinite number of other intermediate times, I can think of an infinite number of these little instantaneous snapshots, and I can stack them all up, and now I get this, what we call space-time diagram. So I hope everybody can just kind of look at that now and say, oh, I see. That's A and B banging off each other. Okay? That's really all you need to do. You just need to be able to kind of visually look at these pictures to interpret what they're saying. Now, in relativity, all of that changes. The first thing we do is we're going to get rid of this absolute time. We're going to get rid of these global instants of time. We're going to get rid of absolute simultaneity. We're going to get rid of the idea that points of space persist through time. We're going to get rid of the idea that anything has an absolute velocity. All of that thrown out the window. Then in the other window, it's not a matter of taking Newton's theory and just eliminating things from it. In the other window, we're going to bring in some stuff that Newton doesn't have, right? Some new structure. Obviously, once you get rid of absolute space and time, you get rid of absolute speeds, so there's not going to be a speed of anything, including a light ray. So if that's true, what do you mean nothing goes faster than light? If there's no speed that light goes, what could that constraint even mean? But fortunately, it's really easy to understand that. Because a new thing that comes in is what we call the light cone structure. Or if you want to impress your friends, you can call it the formal structure. We have a four-dimensional space-time, and we're going to put a kind of geometry on it, a pretty unfamiliar one. And one of the things that geometry defines is, well, what it doesn't define is this slicing up into successive instants. That, again, the fancy name for that is a foliation. We don't have one anymore. Gone. So what do we have? We have the light cone structure. We have a little more than that, but again, a pictorial representation of this is all we're going to need for this. So by using a space-time diagram, I can give you an idea of what a light cone structure looks like. Again, there are three spatial dimensions. I'm going to repress one, and the one thing you have to bear in mind is, of course, the diagram itself is, as it were, a Euclidean diagram, right? The picture is in three-dimensional Euclidean space. It's a picture of a very different kind of space. So there are some places where you could be a little cautious about interpreting it. But for our purposes, it's actually what we need to do is very easy. So we're going to use that, and for what we're going to see is that in this structure, for every event, right, and an event is just going to be a point in this diagram. So again, an event happens at a particular place and time. Every point, there will be associated with it what we call a light cone. So this is a picture out of a book by Sean Carroll, and you see every single point here has a little light cone. Now that light cone doesn't stop, it keeps going forever in this geometry. And once you have this light cone, you can sort of think of time going this way, upward on the diagram. And now we can make distinctions between different paths, which he's done here. So a so-called time-like path, as we say, threads the light cones. At every point, the path is going into the future light cone. Whereas you could imagine paths that cut across the light cones this way. These are called space-like. Now you'll notice Sean says this is allowed. What he means is that's allowed for a particle. A massive particle could do that. This is not allowed. A massive particle can't do that. So you can see how you can state a constraint on matter just given the light cone structure. Notice I didn't use any speeds in saying any of that. If you're still a little puzzled about what this light cone is, maybe this will help. Remember, we're thinking of a little two-dimensional world. And you might wonder, why is it called a light bulb? Imagine I set off a light bulb, a flash bulb, in our world. What happens? Light goes off in all directions, and you would sort of think you get an expanding sphere of light. Well, in a two-dimensional world where I've cut out one of the dimensions, I set off a light bulb, and you would get an expanding circle of light. So if I set off a light bulb here, the future light cone represents where all that light would go. And that's just dictated by space-time itself in this theory. What about the past light cone? Well, the past light cone is telling you if you're at a certain point and you're looking in a certain direction, or you're taking a photograph, you're not now setting off while you're taking a photograph, what is that photograph going to be of? It's going to be of all the light arriving at that point at that time. That's coming in along the past light cone. So this picture really tells you all you need to know about relativity and how, if you have a relativistic space-time, you can make sense of the claim that x does not go faster than light, right? If particles can't go faster than light, I think I have a picture. Yeah, okay. So for particles can't go faster than light, that means all the particle trajectories have to thread the light cone. The later trajectory always lies in the future light cone of any point. It can't pass through, so I've extended out this light cone, and I'm going to show you something a particle cannot do on this. If it can't go faster than light, a particle can't, as it were, suddenly make a turn and pass through the edge of the light cone. So that's a real constraint, right? And what if I say not particles, but causation can't go faster than light? Well, imagine that at this point I press a button. And that pressing that button has effects, right? Maybe it's going to set off a bomb, whatever. Where could those effects be? Well, if causation can't go faster than light, then this cannot be an effect of that, right? Doing this can't make a difference outside the light cone. It can only make a difference inside the future light cone. So we have a clear constraint statable in these terms. It's in terms of those that John Bell formulates his theory. So he says, take any theory. This is not about quantum mechanics. It's not about classical mechanics. It's not about any particular kind of physics. Take any theory where causation can't go faster than light. Right? Take any theory where all the causes of an event have to lie in or on its past light cone, and all of its effects lie in or on its future light cone. And any events out to the side can be neither causes nor effects. Call that a causally local theory, or a Bell local theory. That's the condition of his theorem. If that's true, then when two events lie outside each other's light cones, kind of sideways to each other, we say they're space-like separated, then they cannot be directly causally related to each other. They could, of course, both be effects of a common cause, right? So if this event and this event, they can't directly have effects on each other, but a cause of this event might lie back here, a cause of this event might also lie back here, and they're common in where their past light cones overlap. So there's no problem with there being correlations between events at space-like separation. It's just you would explain those correlations by common causes, and those common causes would lie in their common paths. Okay? So we can call that the condition of relativistic causation. It's obviously very general. If I move from special relativity to general relativity, nothing changes, because in general relativity you also have a light cone structure. It can be wonkier and weirder than in special relativity, but I have a perfectly good light cone structure. What kind of theory does this apply to? Any kind of theory, right? As long as it has causation. You can ask, if that's a constraint. What does Bell prove? He proved, and I really do want to say proved, although everybody who doesn't like this result is looking for every possible loophole they can to get out of it. But none of them are reasonable. That in any relativistically causal theory, there are constraints on the sorts of correlations that you could reliably and predictably observe between outcomes of experiments done at space-like separation. So we're going to have two experimenters, Alice and Bob, or eventually three, Alice, Bob, and Charlie, in their labs doing experiments. Those are going to be in our diagrams at space-like separation, right? Separated out to the side so that nothing that happens in Alice's lab can have an immediate causal effect on Bob. Nothing that happens in Bob's lab can have an immediate causal effect on Alice if it's a globally causal theory. And these constraints are expressed in an equation or a set of equations, because they're a little different in different circumstances, that are called Bell's inequality. And all I want to do in this entire talk is explain what those are and why they're problematic, right? Why violating these constraints is so problematic. Now, we're going to look at a specific case where we have some perfect correlations. You don't need them to do to derive Bell's inequality, and you don't really need to have them to violate it. But if you have these perfect correlations, the whole business becomes much easier. And this idea of looking at perfect correlations goes back well before Bell. It goes back to this famous paper by Einstein, Podolsky, and Rosen, which is the EPR paper, which was written in 1935. In fact, the title of Bell's paper is On the EPR Paradox. He had the setup that Einstein formulated as part of what you were supposed to understand here. And in that setup, in the EPR paper, what they noticed for the first time, even though quantum mechanics had been around for over a decade, was that there were peculiar, one might say, well, whether they're peculiar or not, we'll talk about, perfect correlations that are predicted by the theory between measurements or observations or experiments done arbitrarily far apart in different laboratories. Now, at the end of the day, you might say, I don't think those are very strange at all. They actually didn't think they were strange. But this is how it all starts. So it's in the EPR. So they didn't, when Einstein, Podolsky, and Rosen write this paper, they do not use what we're going to use. We're going to talk about what we call spin measurements. They talked about what are called position and momentum measurements. The fundamental point is the same, but changing to spin, which was originally done, as far as I know, by David Bohm, makes the entire situation much more interesting. So what do I mean by spin? Well, many particles have a feature that goes by the name of spin. It's a kind of, you can think of it as intrinsic magnetic moment, as if the particle was a little bar magnet that has a north and south. How does that show up in the lab? Well, this device is a big magnet. It's called a Stern-Gerlach magnet. You'll notice the geometry of it is it's sharp and pointy. Oops. Man, I can do that by touching. Okay, it's sharp and pointy here. It's not sharp and pointy there. Because of that, these magnetic field lines they kind of curve around this way at the top, and they're a little flat at the bottom. They're inhomogeneous. That's important for the effect. And the natural, what's the prediction of what this magnetic field effect will be on, here's my particles that are being shot at this screen. So here's the classical prediction over here, this little filled-in eye. It says, well, it depends on how that little bar magnet is oriented. If it's oriented exactly in line with this in one way, if it's the south end to the top and the north end to the bottom, you'll be more sharply pulled upward than pulled downward, and it'll be deflected upward. And you get this eye shape because as you go out to the sides, the field dies down. So the eye is just pulling. You get the maximal effect right down the center. So it'll end up here. And if it's flipped over, you get the opposite effect. It'll end up down here. But if it's also on its side like this, everything will balance out and it'll go straight through. So the classical prediction is the particle could end up anywhere in this eye area, depending on the orientation. But the quantum prediction is this one. And this is an instance of what we normally call quantization. That is, every particle will either be, as it were, deflected up the maximal amount or deflected down the maximal amount, nothing in between. So this is very different than the classical prediction. That's the actual historical data that Stern and Gerlach took. This was a postcard they sent to Bohr after they did it, and no magnetic field. Magnetic field, you see the eye open up, exactly what quantum mechanics predicts. What that means is that whenever I do this experiment, I get one of two outcomes. Either, as we say, spin up, that is, it was deflected toward the pointy part, or spin down, that is, it was deflected away from the pointy part. So I can describe these outcomes on every single particle with one of two numbers. We traditionally use +1 or -1. That's just a convention. Good. Now, what kind of states, spin states, can single particles be in? Well, we assign a direction in space for a single particle. It's always got a spin, and that spin always points in some direction. And we can orient our big magnet in any direction we want. So if we orient our magnet in the x direction, we say we're going to check for x spin, And we can prepare a particle in a state we call x spin up, which means if we prepare a bunch of particles that way, they all get deflected up, every single one. We can prepare x spin down. All of those will be deflected down. We can do the same for the y direction or the z direction or any in-between direction. Those are all possible spin states of individual particles. There's an obvious way to write this so you understand this notation. This just means the x spin of the particle is definitely up. This means the y spin of the particle is definitely down. It's an interesting fact, mathematical fact, that the x spin up state and the x spin down state are equal superposition of y spin. So if you make sure you know what's going to happen to the x spin, you become automatically maximally uncertain about the y spin. This is an example of what's called the uncertainty principle. Okay. If we're in any state of definite x spin, you can predict with certainty what will happen if you check the x spin and so on. And that's interesting. Okay, you can get uncertainty principle, you can get some stuff out of that. That's not what drives Bell. If that's all we had, there would be no room for Bell's theory. What now becomes really interesting, and this was the thing that Einstein, Podolsky, and Rosen first realized, is that when you have a collection when you have a system with more than one particle, multiple particles, the spin states available to that go beyond what you'd expect. So what would you expect? Well, you would say, look, suppose I have two spin-half particles. Spin-half just means they either go up or down. What kind of quantum states can that pair be in? Well, obviously, if I can prepare this particle x spin up and I can prepare that particle y spin down, then they could be in a state where this one's x up and that one's y down. Those are called product states. They're just what you'd expect. Take any spin state a single particle can be in, put this one in this state, put that one in whatever other state you like. Those are available. Nothing funny is going to happen from those. And those are just called the product states. And again, the symbolization is easy here. If I make Alice's particle x spin up and also Bob's particle, then it's that state. If I make Alice's particle x spin up and Bob's particle x spin down, it's that state. If I make Alice's y up and Bob's x up, it's that state. So you can, again, you don't have to know a lot, just read off of this notation. But essentially what Einstein, Podolsky, and Rosen pointed out, and what Schrodinger, who responded to their paper, reacted to their paper with the famous cat paper, Schrodinger was pretty shocked by what they discovered. And he thought deeply about it and was very puzzled. And he introduces the term that we translate entanglement. He said, the weird thing is that there are these entangled states. This is what's new in quantum mechanics. This has no classical analog. None of this happens in classical physics. It's, as I said, Schrodinger wrote in that paper that it was entanglement, right? Not the uncertainty principle, not the lack of the introduction of probabilities or anything. That was the feature of quantum mechanics that, quote, forces a departure from classical lines of thought. And there's a particular state of a pair of spin-half particles that we're going to be concerned with. This is the one that Bell used when he proves his original theorem. It's written like this. It's called the singlet state. So it's 1 over, you put in front of it 1 over root 2. Now this is a regular product state. This is a state where Alice's particle is x spin up and Bob's is x spin down. Minus, that minus turns out to be important, but we're not going to talk about that. 1 over root 2, Alice down, Bob up. Right? So as it were, 1 over root 2 this, minus 1 over root 2 that. That's a single state. That cannot be written as a product state. It cannot be written as this spin state for Alice and this spin state for Bob. That's why they're entangled. Somehow you can't even specify Alice's particle without referring to Bob's, or Bob's particle without referring to Alice. What would you predict if you started measuring spins on a pair of particles in this state? Now the nice thing about it, there's the state up there. The nice thing about it is you can kind of just read it off this diagram. If they both decide to check for x spin, what does the theory predict? Well, basically, you take these numbers that I've stuck out front. You'll notice if I square these, I get a half. If I square them and add them up, I get 1. That's important. Essentially, the idea is, if I square this, a half, there's a 50% chance you'll get this result, that is Alice up and Bob down, and a 50% chance you get that result, that is Alice down and Bob up. And then you can change that to 1/2, root 3 over 4. You can move those probabilities around as you like. The minus sign, you say, why the minus sign? What if I put the plus sign? For that particular experiment, it wouldn't matter. You'd get the same prediction. But if you then change directions, the predictions would change. And so, again, if you don't know, even if you don't know the first thing about quantum theory, you can just kind of stare at that and say, oh, I know what that predicts. Now, what you notice about that, what Einstein, Podolsky, and Rosen notice about it is, look, this predicts, even though it doesn't predict exactly what will happen, whether this or this, it predicts with certainty that you'll get opposite results. Right? That whatever Alice sees, Bob will see the other thing. That's a perfect correlation. Right? That's a 100% correlation. They will certainly get opposite results. It turns out that's true for this state if they both measure in the same direction, no matter what the direction is. If they both measure in the y direction, they'll certainly get opposite results. If they both measure in the z direction, they'll certainly get opposite. All right, so those perfect correlations we call EPR correlations after Einstein, Podolsky, and Rosen. Why? Because they're perfect, they allow you to do a deduction with certainty. Once Alice sees her result, she can now predict correctly with certainty what Bob got or will get, and the other way around. That prediction with certainty is important for the logical structure of the argument that Einstein, Podolsky, and Rosen give. They both know how they've been prepared, how the particles have been prepared. Neither of them knows what to expect when they do their own experiment. They're going to be, 50-50 heads or tails. They don't know what's going to happen. But once it has happened, once what's happened in their lab has happened, they now know what happened in the other lab. Even though the state itself doesn't determine that, right? Even though according to quantum mechanics, that quantum mechanical state doesn't tell you what will happen in either lab. Now, question, how can I account for that? How can I account for always there being these opposite results? Is that spooky? Is that weird? Is that strange? Not in the least. Not at all. There is absolutely nothing surprising or shocking about the existence of these kinds of perfect correlations between these experiments. And Einstein was completely, no, there's nothing weird about this. This is not a paradox. Nothing weird about this. People often give just examples, right? All you're saying is when Alice gets in her apparatus, if it's set in a certain direction, Bob will get the opposite when his is set in that direction. And you say, look, people always give these examples. Take a dollar bill, tear it in half, put each half in an envelope, shuffle them behind your back, send this one off to Alice, that one off to Bob. You don't know, Alice doesn't know, Bob doesn't know what they'll see when they open their envelope, but gee, if she has the right half, she immediately knows Bob has the left half. Right? There's nothing spooky or weird or strange about that at all. So what's the big deal, right? Why is Einstein making such a big deal about that? He's making such a big deal because the explanation I just gave you, the commonplace one, is also deterministic, right? The idea is already when I put the bills in the envelopes, I put the right-hand one in one and the left-hand one in the other. And it was already determined at the source what Alice would see and what Bob would see, right? So that explanation is commonplace, but also of necessity deterministic. There can't be any fundamental chanciness or probabilities here. The theory, the envelope theory, is locally causal in our sense, but suppose you said, no. The fundamental laws of nature are not deterministic at all. Suppose you said with Bohr and the Copenhagen people, God plays dice, right? The fundamental laws of physics are chancy. Suppose you said that before Alice opens her envelope, there's no fact of the matter about which side of the dollar bill is in it. And that something fundamentally random and chancy will happen when she opens the envelope. That all of a sudden you see either this one or that. That's weird. Right? I mean, that's weird just to say, why should her opening the envelope have this profound effect? But it's even weirder. The point is it's even weirder. Because not only does her opening the envelope suddenly make this half be one half, it makes Bob's half be the other half. Right? John Bell, again, gave a beautiful example in a nice paper called Bertelsmann's Socks and the Nature of Reality. His friend, the physicist Bertelsmann, for some reason or other, decided when he was young he would always wear different colored socks. So he gets up, and this is apparently quite true, he gets up every morning, he puts on different colored socks. You can't predict on any given day what the color of any sock will be, and he has a nice diagram that he wrote, or picture that he wrote of Bertelsmann walking into the room, and you see a pink sock, and then you say, well, I now know something about the other sock, it's not pink. And Bell says, nothing weird about that. But what if you said, before you looked, neither sock had any color at all? And he says, it's as if a child had asked, but then how does the one sock know what the other sock has done if they always have to have different colors? So this is a situation where, in a deterministic theory, it's easy to explain these perfect correlations. But if you try to introduce fundamental indeterminism into the theory, it gets weird and spooky and strange and telepathic, as Einstein would say. That's what he called spooky action at a distance. That somehow Alice doing her experiment in her lab not only has an effect on her particle, nothing weird about that, but she has an effect on Bob's particle. Way over there at space-like separation, so far away that not even light could get it. All right? So this is the reason why we do these experiments at space-like separation, is to make sure that if in a causally local theory, nothing that happens over here can have an effect over here, and vice versa. Good. So here's the moral of the EPR paper, that if a theory is causally local and it displays these perfect correlations, which is predicted by quantum mechanics, then the theory must be deterministic. It's not an assumption that physics has to be deterministic. It's a conclusion. It's a theorem that if you want to preserve local causality and you have these perfect correlations, you are forced into a deterministic theory. That's, of course, trouble for quantum mechanics as Bohr and Heisenberg and the Copenhagen people understood it, because they understood it to be fundamentally a non-deterministic. If you want to maintain local causality, it has to be the initial preparation of the experiment, has to predetermine the outcome of each experiment so that you don't need any causal influence on them. That's the only way to preserve local causality in the face of these perfect correlations that allow you to predict the outcome of one experiment from the outcomes of the other experiment. That's part one, the big part one, coming out of the EPR paper, of the conclusion that's correct, that you ought to draw. Einstein, for all his effort, could not get Bohr to understand this. If you read Bohr's response to the EPR paper, it's a bunch of gibberish. He doesn't get the point. He never responds to the point. It's sad. Now, what does Bell show? Bell shows that that's fine for these perfect EPR correlations in the example Einstein, Podolsky, and Rosen give. But if you look at the full range of quantum mechanical predictions, you cannot explain them with any locally causal theory. Okay? Now, Bell's own argument actually ran off of this singlet state that we talked about, and it involves certain kinds of probabilistic or statistical predictions. It's right, the argument's correct, it doesn't take too long, but I'm going to skip over what Bell actually did to this example later discovered by Greenberger, Horn, and Zeilinger, so-called the GHZ example, because it's just logically nicer we're going to change our situation a little bit. Before we were talking about pairs of particles, one being sent to Alice, one to Bob. Now we're going to have a triple of particles, one sent to Alice, one to Bob, and one to Charlie. Okay? And we're again going to say, here's something that they could not see if the theory, whatever it is locally causal. If causes can't go faster than light. Okay? And as I say, this isn't the one Bell used, but that's okay. This one's nicer. So here's the picture. We're almost done. This is the big payoff. If you followed everything up until now, just pay attention for another 5 minutes. If you don't know this stuff, you should be astonished. If you're not astonished, you didn't get it. Okay, so here's the situation. I have now a source here in the center that sends out a triple of particles prepared in a certain state. One to Alice, one to Bob, one to Charlie. They can be separated as far as the theory goes, as far as you like. They could be 100 billion miles apart in their labs. Each of them has a Stern-Gerlach device. They could, in principle, orient it in any direction. We're going to restrict them so they have the free choice on any given run of this experiment to orient it either in what we'll call the z direction or at right angles in the x direction. Okay, so either this way or that way for each of the three. They can make that decision any way they want. They can do it, as we say, at a whim. They can flip a coin. They can do it on the basis of the parity of digits of pi as expressed in base 37, starting with the billionth digit, whatever you want. Anything you would think of as a random method of choosing, right? You don't want any pattern in what they're doing. And they can make their choices. They make them independently of each other in whatever way they like. What does that mean? Well, every time you run the experiment, you'll get one of 8 experimental situations because you've got three binary choices. So maybe they all happen to measure x, or maybe this one measures x and no z, and there are obviously 8 possibilities. We're going to have the predictions of quantum mechanics for these experiments. Quantum mechanics, for the special state you can prepare, makes the following prediction with certainty. Again, this is not a probabilistic prediction. This is with certainty. So this is an EPR correlation. If they happen to all set their detectors in the x direction, which we'll just represent in this obvious way, x1, x2, x3, or A, x, B, x, C, Alice, Bob, and Charlie, there will certainly be an odd number of up outcomes. Now, the theory doesn't predict whether that odd number will be 1 or 3. It could be either of those. And it will even give you statistics for how often it would be 1 and how often it would be 3. We don't care. The whole math of this thing, the only deep mathematical principle you need to understand this argument is the difference between even and odd. Okay? So if you check always in the x, all 3 in the x direction, for sure you'll get an odd number of up outcomes. All the time. However, if one of them happens to choose x and the other two choose z, which can happen in 3 ways, depending on who chooses x, then you get another prediction with absolute certainty. You will always get an even number of up outcomes. Could be 0, could be 2. We don't care. It'll for sure be even. Now, just absorb that. That's it. All the phenomena that run into this argument are encapsulated here. Now, you might say, but wait, there's 8 possible experimental conditions, right? Maybe they all pick z. What about those? Well, the theory makes predictions about those. We don't care. All we care is about, you can just ignore those. They don't matter. We're just interested in what happens if they happen to do this or they happen to do one of those 3 things. Okay? This way, always an odd number. This way, always an even. Okay, so what? First conclusion. Now we go back to our EPR argument. just by the same reasoning that we used in the EPR case. If you want to say that the way Alice's magnets are oriented can have no effect on Bob or on Charlie, and vice versa, right? None of their choices can have any influence on the outcomes that the others see. Then by exactly the same argument we gave before, the outcomes have to all be predetermined. Why? Because from any two outcomes, you can predict the third, right? If you know they all chose X and you know two of the results, you know what the other one has to be, because it's got to be odd. And so by exactly the same argument, you say, well, if something risky or chancy or indeterminate happened in Bob's lab, how do Alice and Charlie's particles know about it? Right? How can they always act in a way to produce this result? So we're not yet forced into denying causal locality, but we are forced in saying if it's a causally local theory, it better be deterministic. Right? That is, the outcomes of these experiments have to already be predetermined at the source. Right? That's our first conclusion. Nothing can happen by chance. And this is it. This is the end of the whole story. As I like to say, this thing, you think of this as a cocktail napkin. Because if you're at a cocktail party, you want to impress people, and you have a pen, draw this. This is a nice diagram of the situation as far as I know. This explication, and this is, I think, due to David Berman. Notice what we have on this diagram. This circle represents Alice, 1. Oops. Touch that thing. Oops. This circle represents Alice setting her device in the x direction. This one represents Bob setting his device in the x direction. Charlie in the x direction. Charlie in the z direction. Bob in the z direction. Alice in the z direction. So there are only 6 possible ways for these different apparatuses to be oriented. They're all represented here. And then you'll notice, because of the way these have been put down, this dotted line represents the situation where all 3 choose X. The 3 solid lines represent the 3 different situations where one chooses X and the other chooses Z. So our predictions have to do with what if it's like this, what if it's like this, what if it's like this. Question. Very simple question. Can you prearrange these outcomes so that no matter what Alice, Bob, and Charlie happen to choose, their outcomes are in accordance with our predictions? Or another way to put it, can you write the letters U and D in these 6 circles in such a way that there are an odd number of U's along that row and an even number of U's along the other 3? Well, let's give it a shot. Let's just try. I want an odd number along here. It's got to be 1 or 3. Let's just pick 3 because then I don't have to make any choices. U, U, U. Okay. Now, if they're predetermined to do this and they happen to all pick X, we're fine. What about this guy? No real constraints on that. I'm tired of U, so I'll just put D in there. What the heck? Now our constraints bite. Now I have no further choices. I need an even number of U's along this row. It means I must put a U there. Only one left, but if you're paying attention, you're screwed, right? Because if I need an even number along here, I have to put in a U, but if I need an even number along here, I can't. Can't fill it in. That's it. You cannot escape from that conclusion. That's all the mathematics that goes into this. It is mathematically, logically impossible to pre-assign these outcomes in such a way that no matter which of these experimental situations is chosen, you'll get the results predicted. Which means no locally causal theory can predict what quantum mechanics is. No theory where nothing goes faster than light, in particular no causal influence goes faster than light, can make these. And, of course, what's really important is not so much that quantum mechanics predicts it, it's that that's what nature does. People who check, this has been checked in the lab, I mean, first with Bell's example with only 2 particles, and then they haven't even checked this 3-particle thing. A couple of years ago, the Nobel Prize in Physics was given to experimenters who did these experiments and verified the prediction of quantum mechanics. And again, you can throw away quantum mechanics tomorrow, but you're not going to throw away those lab results. They are what they are. And they are not compatible with locality in Bell's sense. Bell should have gotten, of course, Bell should have gotten the Nobel Prize. I can't go past this without saying he died, unfortunately, before they had the sense to award this prize. Awarded it to the experiment. So, conclusion, no local and causal theory can't be believed. And then, you know, the further consequence, if you understand relativity as saying nothing can go faster than light, and among the nothings that can't go faster than light is causation, then it looks like you're in a flat contradiction. So on that reading, our fundamental theory of space-time and our fundamental theory of matter are not just kind of a little wonky with respect to each other, but they're a flat contradiction. So there's just no obvious way. I mean, I'm putting obvious in because there are lots of very fancy, you know, gymnastics that people have tried to do to get out of this. There's a lot of just nonsense people have said to try to get out of it, and there's some fancy mathematical stuff. Anyway, there's just no way a theory can admit of non-local causal connections. That they've got to do, right? They have to have non-local causal connections. There's no obvious way that you can do it without bringing in some space-time structure that we got rid of in going from Newton to relativity, right? Remember, Newton had this nice absolute simultaneity, this foliation of space-time. If you give me that back, I can write down like that some equations that will make these predictions. Where, in fact, what Alice does affects what Bob sees, or what Bob does affects what Alice sees. But if you don't bring that back, it's very hard to even write down a theory as convoluted and as you try to make it that will make these predictions. It looks like we need something like the structure of absolute simultaneity that Newton postulated to get out of this. I personally think that's the correct conclusion. I personally have a theory of space-time structure like that. Again, this is not a conflict, I like to say, between relativity and quantum theory. It's a conflict between relativity and the actual outcomes of laboratory experiments. So, you know, when you ask who's going to win. But certainly, I think we can say without a resolution to all this, we can't complete physics because we're dealing, you know, we're using theories that actually really don't fit together.